In this module, we will learn about development of chemistry and the concept of matter. Introduction. Science is a continuous human effort to organize the knowledge in the form of testable explanation and understanding of the nature. Science can be classified in the following parts. Here, we will study about a special branch of science, that is, chemistry. Chemistry is the branch of science where we study the compositions, properties and interactions of matter. Development of chemistry. Chemistry was not studied as a subject in earlier days as it is done today. In fact, it evolved during the search for two interesting things: philosopher's stone, which would convert all baser metals like iron and copper into gold, and elixir of life, which would grant immortality. Ancient Indian people had the knowledge of many scientific phenomena. During 1300 to 1600 Common Era, chemistry was developed in the form of alchemy and iatrochemistry. After a few centuries of alchemical traditions which were introduced in Europe by the Arabs, modern chemistry took shape in the 18th century. Chinese and Indian cultures had their own alchemical traditions, which included much knowledge of chemical processes and techniques. Chemistry was called as Rasayan Shastra, Ras Tantra, Ras Kriya, or Ras Vidya in ancient India, which also included metallurgy, medicine, manufacture of cosmetics, glass, dyes, etc. Systematic excavations at Mohenjo-daro in Sindh and Harappa in Punjab verify that the development of chemistry in India is very old. Show that baked bricks were used for construction. It also shows production of pottery on large scale. The earliest chemical process of producing pottery of desirable qualities was done by subjecting wet molded clay to heat obtained from fire. In Mohenjo-daro, remains of glazed pottery have been found. They used gypsum cement also in the construction work, which contains lime, sand and traces of calcium carbonate. Harappans also made faience, which they used in making ornaments. Faience is a type of glass. They also melted and forged a variety of objects from metals, such as lead, silver, gold and copper. They also improved the hardness of copper for making artifacts by adding tin and arsenic to it. 1000 to 900 before Common Era, a number of glass objects were found in Maski in South India. Glass objects were also found in Hastinapur and Takshila in North India in 1000 to 200 before Common Era. The glass and glazes were also colored by adding coloring agents like metal oxides. Metallurgy of copper in India dates back to the beginning of Chalcolithic cultures in the subcontinent. Many archaeological evidences support the view that the technologies used for the extraction of copper and iron were developed indigenously. According to Rig Veda, tanning of leather and dyeing of cotton were used during 1000 to 400 before Common Era. The golden gloss of the black polished ware was found in northern India. Even today, it could not be replicated and is still a chemical mystery. Many statements and material as described in the ancient Vedic literature can be shown to agree with modern scientific findings. Let's know about some of them. In Kautilya's Arthashastra, the production of salt from sea water is described. Copper utensils, ornaments of iron, gold, silver and terracotta discs and painted grey pottery have been found in many archaeological locations in North India. Importance of alkalis is explained in Sushruta Samhita. Charak Samhita explains the preparations of acids such as sulfuric acid, nitric acid, and oxides of copper, tin and zinc. Preparation of sulfates of copper, zinc and iron and the carbonates of lead and iron is also mentioned in Charak Samhita. The preparation of gunpowder, a mixture, is explained in Rasopnishada. The preparation of fireworks using sulfur, charcoal, saltpeter, potassium nitrate, mercury, camphor, etc. is explained in many Tamil texts. Arjuna was a great Indian scientist, reputed chemist, an alchemist and a metallurgist. His book Rasratnakar explains the formulation of mercury compounds. He also discussed methods for the extraction of metals like gold, silver, tin and copper. Uses of various furnaces, ovens and crucible for different purposes is explained in a book named as Rasarnavam, written around 800 Common Era. It also describes methods by which metal could be identified by flame color. Sulfide. He invented soap also by using mustard oil and some alkalis. Indians began making soaps in the 18th century Common Era by using oil of erund and seeds of mahua plant and calcium carbonate. The paintings found on the walls of Ajanta and Ellora, which look fresh even after ages, prove that the level of science was very high in ancient India. Varamihir's Brihat Samhita was composed in the 6th century Common Era. It is a sort of encyclopedia. It gives information about the preparation of glutinous material to be applied on walls and roofs of houses and temples. This glutinous material was prepared entirely from extracts of various plants, fruits, seeds and barks which were concentrated by boiling and then treating it with various resins. Many classical texts such as Atharva Veda also mentioned about some dye stuff. The material used in them were turmeric, madder, sunflower, orpiment, cochineal and lac. Patanga and Jatuka also have coloring property. Varamihir's Brihat Samhita also gives references to perfumes and cosmetics. Recipes for hair dyeing were made by using plants such as indigo and minerals like iron power, black iron or steel and acidic extracts of sour rice gruel. Gandhayokli explains about methods for making scents, mouth perfumes, bath powders, incense and talcum powder. According to the account given by Chinese traveller I Sing in India, paper was known in the 17th century. Excavations at Takshila prove that ink was used in India from the 4th century. Chalk, red lead and minimum were used for making colour of the ink. Indians knew about the process of fermentation very well. Vedas and Kautilya's Arthashastra describe about many types of liquors. Charak Samhita also mentions ingredients such as bark of plants, stem, flowers, leaves, woods, cereals, fruits and sugarcane were also used for making asavas. Very small indivisible particles which he named as Parmanu. He wrote the text Vaisheshika Sutras. According to him, all substances are aggregated form of smaller units called atoms, Parmanu, which are eternal, indestructible, spherical, suprasensible and in motion in the original state. Kanad explained that this individual entity cannot be seen through any human organ. He also said that there are varieties of atoms that are as different as the different classes of substances. He said these could form pairs or triplets among other combinations and unseen forces cause interaction between them. He gave this theory around 2500 years before John Dalton. Charaka Samhita is the oldest Ayurvedic classic written in India. It explains the treatment of various diseases. The concept of reduction of particle size of metals is also explained in Charaka Samhita. Extreme reduction in the size of particle is termed as nanotechnology. Charaka Samhita explains the use of bhasma of metals like gold in the treatment of ailments. Nowadays, it has been proved that bhasmas have nanoparticles of metals. After the alchemy, iatrochemistry reached a steady state. Later, it declined due to the introduction and practice of Western medicinal system in the 20th century. During this period, pharmaceutical industry based on Ayurveda existed, but it also declined gradually. Indians adopted new techniques in next 100 to 150 years. During this time, India had many foreign products. As a result, indigenous traditional techniques declined as the time passed. In India, modern science appeared in the later part of the 19th century. European scientists began to visit India by the mid-19th century, and modern chemistry started growing. We see that chemistry deals with the composition, structure, properties, and interaction of matter. Therefore, it is very useful for human beings in everyday life. These aspects can be understood in terms of basic constituents of matter that are atoms and molecules. Therefore, chemistry is also called the science of atoms and molecules. Effort to organize the knowledge in the form of testable explanation and understanding of the nature. Chemistry is the branch of science where we study the compositions, properties and interactions of matter. Indian people had the knowledge of many scientific phenomena in ancient time. According to Rig Veda, tanning of leather and dyeing of cotton were used during 1000 to 400 before Common Era. The first proponent of the atomic theory. According to Kanad, all substances are aggregated form of smaller units called atoms, which are eternal, indestructible, spherical, suprasensible and in motion in the original state. Chemistry is also called the science of atoms and molecules.
Measurement and significant figures. In this module, we will study about matter, mixture, pure substance, measurement, measuring unit, uncertainty in measurement, precision and accuracy, significant figures, and dimensional analysis. An introduction.
Science can be viewed as a continuous human effort to systematize the knowledge for unfolding and understanding the nature.
Easier understanding. Science is subdivided into various disciplines. Chemistry is one of them. Is the branch of science that studies about the compositions, different properties and various interactions of the matter. It plays the central role in science as it is often connected with the other branches of science like physics and biology. Plays a significant role in meeting the human needs for food, healthcare products, and other stuff for better living. With a better understanding of the chemical principles, scientists have successfully designed and synthesized new materials having specific magnetic, electric, and optical properties. Understand the basic concepts of chemistry, which has led to such great inventions. Recall the story of Thirsty Crow. Do you know why the layer of water rose on putting the pebbles into the pitcher? By space and has weight is called matter. can exist. Solids have a definite shape and volume and have very less intermolecular spaces. Ice is the solid form of water. Liquids have a definite volume but not definite shape. Definite volume or shape. Three states of matter. Depending on the existence, matter can be classified into pure substances and mixtures. You relish having lemonade, which is a mixture in scorching summer. You can feel the presence of each and every ingredient from which it is formed.
Mixture. Is made up of two or more substances. A mixture is said to be heterogeneous if its composition is not uniform throughout. A mixture is said to be homogeneous if its composition is uniform throughout. Is made up of only one kind of atom, that is, silver atom. Water is made up of a fixed ratio of hydrogen and oxygen atoms per molecule. Pure substances contain only one type of substance. They always have the same properties. Substances are further classified as elements and compounds. Elements consist of the same types of atoms having identical and definite chemical and physical properties. When different elements or same elements combine together, a compound is formed. A compound contains two or more than two elements. substance has a unique or a characteristic property. Properties. They are observed or measured without changing the identity or composition of the substance. For example, density, volume, mass, color, odor, etc.
Anything that has mass and occupies space is called matter. Matter is everything around us. Matter can exist in three states: solid, liquid, and gas.
Measurement.
Let us measure the length and breadth of a rectangle to find its area.
Unit.
Given in the previous slide, we can now define a unit. Is defined as the standard of reference chosen to measure any physical quantity. The International System of Units has 7 fundamental units. It's of some basic physical quantities.
Current from the given options, which are A. Ampere, B. Candela, C. Mole, D. Kelvin.
The unit of length is defined as the length of path traveled by light in vacuum during a time interval of 1/299,700,000 kilogram. The unit of mass is equal to the mass of the international prototype of the kilogram. The unit of time, 1 second, is the duration of 9,192,631,770 periods of the radiation corresponding to the transition. Unit of current. Constant current which, if maintained in 2 straight parallel conductors of infinite length, of negligible circular cross-section, and placed 1 meter apart, is of amount of substance. It is the amount of a substance of a system which contains as many elementary entities as there are atoms in 0.012 kilogram of carbon-12. The unit of luminous intensity. It is the luminous intensity in a given direction of source that emits the monochromatic radiation of 540 into 10 to the power 12 Hz frequency, and that has a radiant intensity in the direction of 1 upon 680.
Most of the time we use mass and weight as synonym. Is it correct? Kilograms on Earth weighs 19.6 newtons. Mass is the quantity of matter contained in the sample. Weight is defined as the force exerted on an object by the pull of gravity. The amount of space occupied by this box. We will fill this box with small cubes of volume 1 centimeter cube. This box into 4 equal layers and calculate its volume again, we will observe that the volume of each layer comes out the same, centimeters cube. When we add the volume of all the layers, it comes out to be 60 centimeters cube. The three-dimensional space occupied by any solid, liquid or gas is called the volume. Is used for measuring volume. The amount of a substance contained within a specific volume is known as density. The physical property of a system that underlies the common notions of hot and cold is called temperature. Height by the following expression. Unit of luminous intensity from the given options, which are A ampere, B candela, C mole, D Kelvin. in measurement. The average distance between Sun and Earth is 9,29,35,700 miles. And the atomic radius of hydrogen are very big figures. A number, say p, may be expressed as follows. If p is very much greater than 9.999, then the decimal point is shifted left until there is only one non-zero digit before it. When p is equal to 14,85,679.2, if p is quite less than 1.000, when p is a number in a scientific way. Let us do some mathematical op. Step 3. Count. We can write the number in a scientific way. Write the following number in a scientific way. We can write the number in a scientific way. Write the following number in a. We can write the number in a scientific way by simply following the given series of steps. Step 1. Shift decimal left, ensuring that there is only one number before it. Step 3. Count how many places you shifted the decimal n. Let us do some mathematical operations on numbers expressed in scientific notations. Is subtracting the power of 10 of the number in the denominator from the power of 10 of the number in the numerator. The numerator is divided by the denominator. Following example. That the numbers are written in such a way that they have the same exponent. Following example. That the numbers are written in such a way that they have the same exponent. Following example.
Measurement involving the counting of whole numbers of identifiable objects such as eggs, bananas, tables and chairs can be known accurately, that is, they consist exact number. For many scientific measurements involving some measuring devices cannot be known accurately, that is, they consist approximate numbers. For example, measuring the length, weight, etc.
Precision and accuracy.
With darts in your childhood. When a player in multiple attempts is able to throw a dart on the board closer to the target, the player is said to be precise. Precision is defined as the closeness of many measurements that results for the same quantity. On the other hand, accuracy is defined as how closely a measured value agrees with its correct value. 3 students were asked to take the reading of the solution poured in a measuring cylinder. Addition 9.7 or 9.70 are the same. .70 milliliters means the measurement is accurate to within 1/100th of a milliliter.
Says. Every experimental measurement has some amount of uncertainty associated with it. The uncertainty in the experimental or calculated values is indicated by mentioning the number of significant figures.
For the determination of significant figures, rule number 1. All non-zero digits are significant. Rule number 2. If zeros are sandwiched between non-zero digits, the zeros become significant. Rule number 3. Zeros at the beginning of a non-zero digit figure are not significant. Rule number 4. All the zeros placed at the end of a number are significant provided they are on the right side of the decimal point.
Following numbers with the number of significant figures. Of numbers with significant figures are as follows. Addition and subtraction with significant figures. When measurements are added or subtracted, the result cannot have more digits to the right of decimal points than either of the original numbers. Multiplication and division with significant figures. When measurements are multiplied or divided, the result will contain no more significant figures than the original measurement with a few significant figures. Rounding off the numbers. If the rightmost digit to be dropped is more than 5, the preceding number is increased by 1. If the rightmost digit to be dropped is 5, then the preceding number is not changed. If it is an even number, but is increased by 1 if it is an odd number. Analysis.
Dimensional analysis is the calculation involving the use of dimensions of the different physical quantities involved. On applying unitary method, we get
fundamental units included in the international system of units from the given options, which are A6, B7, C9, D5. Of many measurements that results for the same quantity is known as. The options are A. Accuracy, B. Significant figures, C. Precision, D. Uncertainty. Quick recap. All substances contain matter which can exist in 3 states: solid, liquid or gas. Many systems of measurement exist, out of which the English and the metric systems are widely used.
In this module, we will study about laws of chemical combination, which include law of conservation of mass, law of definite proportions, law of multiple proportions, law of reciprocal proportions, Gay-Lussac's law of gaseous volume, and Avogadro's law, along with Dalton's atomic theory.
An introduction.
Is the branch of science that deals with the composition, various properties and interaction. The entire universe is made up of matter. Everything around us, like book, pen, table, rod, water, air, sugar, etc. is matter.
Combination.
Chemical combination are as follows: law of conservation of mass, law of definite proportions, law of multiple proportions, law of reciprocal proportions, Gay-Lussac's law of gaseous volume, Avogadro's law. Law of conservation of mass, law of definite proportions, law of multiple proportions, and law of reciprocal proportions deal with the mass relationships of the elements. The Gay-Lussac's law of gaseous volume deals with the volume of reacting gases and the gases produced. Let us discuss these laws one by one.
Law of conservation of mass.
According to the law of conservation of mass, during any physical or chemical change, the total mass of the products is equal to the total mass of the reactants.
During a chemical change, matter is neither created nor destroyed. Consider the following example. 100 grams of mercuric oxide on decomposition gives 92.61 grams of mercury and 7.39 grams of oxygen. On calculating, we observe that the total mass of reactants is equal to the total mass of products, which is equal to 100 grams. Here is another example where we observe that the total mass of reactants is equal to total mass of products. Let us solve a numerical. If 8.3 grams of sodium bicarbonate is added to 21.1 grams of acetic acid solution, the residue, that is sodium ethanoate, and water is found to weigh. According to the question, we can write the equation as follows. Now, we will calculate the mass of the reactants. The sum of the mass of reactants comes out to be 29.4 grams. Antoine Lavoisier established the law of conservation of mass. He carefully weighed the reactants and products of a chemical reaction in a sealed glass vessel. He explained that matter can change its state in a chemical reaction, but the total mass of the matter is same at the end as at the beginning of every chemical change. He heated precise amount of water to steam, which was brought into the contact with a red-hot iron barrel embedded in coal. The steam was cooled at another end in the form of water. The amount of water collected was less than that of used in the beginning. Simultaneously, a gas was also collected and the weight of iron barrel also increases. when increased weight of iron barrel and gas was combined, it was observed that this combined weight was exactly equal to the weight of lost water. He also observed that the gas collected was lighter than the air and it was flammable. The law can be verified with the help of Landau's experiment. Landau took the solutions of sodium chloride and silver nitrate separately in two limbs of H-shaped tube known as Landau's tube. The two solutions were mixed by shaking the tube. Reaction occurred and a white precipitate of silver chloride was obtained. After the reaction, the tube was again weighed. It was observed that the weight remains practically unchanged. Take an example of mercuric oxide. 100 gram of mercuric oxide on heating gives 92.61 gram of mercury and 7.39 gram of oxygen. Hence, total mass of reactant is equal to total mass of products. Similarly, when 12 gram of carbon is burned with 32 gram of oxygen, it gives 44 gram of carbon dioxide. Hence, this law explains that in a chemical reaction, the total mass does not change.
To the law of definite proportions, a chemical compound always contains the same elements that are combined together in fixed proportion by mass.
Consider the following example. Carbon dioxide can be prepared by the following methods: by burning coal in air, by heating limestone, and by heating sodium bicarbonate. Thus, the given information can be summarized as follows. Let us solve a numerical. A sample of magnesium carbonate was found to contain 38.5% of magnesium, 24.2% of carbon, and 67.1% of oxygen. According to the law of constant proportion, both the samples will have the same composition. Hence, the masses of magnesium, carbon, and oxygen in 30 grams of magnesium carbonate will be: mass of carbon is equal to 7.26 grams, mass of oxygen is equal to 20.13 grams. Hence, the mass of magnesium in 30 grams of magnesium carbonate is 11.55 grams. The mass of carbon.
Good morning, students.
Good morning, ma'am.
Let's start our chapter. Today we will learn about an important law, but before that, Harry, tell me the 3 different sources of water.
Ma'am, 3 water sources are rain, sea, and well.
Do you think that water obtained from these sources is different?
Yes, ma'am. Rainwater acts as an atmospheric purifier and it contains lots of pollutants. Well provides us with groundwater. It contains minerals such as iron, arsenic, etc. Seawater contains dissolved salts, or we can say that seawater is saline in nature.
But Harry, Do you know that the chemical composition of water is always same irrespective of its source? Let me explain it to you through the law of constant proportions. This law was given by Joseph Proust in 1779. The law states that a chemical compound always consists of the same elements combined together in the same proportion by mass, independent of the method by which it is prepared or the source from which it is obtained. There is a chemical compound AmBn which is made up of two elements A and B. Atomic mass of A is XU and atomic mass of B is YU, where U is unified atomic mass unit. So, mass of M atoms of A is MXU and mass of N atoms of B is NYU. Ratio of mass of element A and element B is mass of A upon mass of B, that is equal to mx upon ny. Now take example of water. Angel, what is the molecular formula of water?
Ma'am, it is H2O.
Good. Water is a compound made up of two elements, hydrogen and oxygen. Atomic mass of hydrogen is 1U and atomic mass of oxygen is 16U. So mass of two atoms of hydrogen in water is 2U and mass of one atom of oxygen in water is 16U. Ratio of mass of element hydrogen and element oxygen is mass of hydrogen upon mass of oxygen, that is equal to 2 upon 16, that is 1:8. It shows that water is always found to contain hydrogen and oxygen combined in the ratio of 1:8 by mass, and this ratio is independent of the source of water. Similarly, we can find out the ratio of nitrogen and hydrogen in ammonia. Good. Children, all of you look at the board and verify your calculations. Ammonia is a compound made up of two elements, nitrogen and hydrogen. Atomic mass of nitrogen is 14U and atomic mass of hydrogen is 1U. So mass of one atom of nitrogen in ammonia is 14U and mass of 3 atoms of hydrogen in ammonia is 3U. Ratio of mass of element nitrogen and element hydrogen is mass of nitrogen upon mass of hydrogen, that is equal to 14 upon 3, that is 14:3. Ammonia is a compound which is made up of two elements, nitrogen and hydrogen, combined in the ratio of 14:3 by mass. Irrespective of that, it is prepared by Haber's process or any other chemical method or produced by animals as excretory waste. A particular compound can be prepared by various independent methods. For example, compound calcium oxide can be prepared by the following 3 methods. By heating calcium carbonate strongly, by heating calcium hydroxide strongly, by heating calcium nitrate strongly. Now find out the ratio of calcium and oxygen in calcium oxide. Good. Calcium oxide is a compound made up of two elements, calcium and oxygen. Atomic mass of calcium is 40U and atomic mass of oxygen is 16U. So mass of one atom of calcium in calcium oxide is 40U and mass of one atom of oxygen in calcium oxide is 16U. Ratio of mass of element calcium and element oxygen is mass of calcium upon mass of oxygen, that is equal to 40 upon 16, that is 5:2. After analyzing calcium oxide prepared by different methods and sources, it is clear that it contains the elements calcium and oxygen only, and they are in the ratio of 5:2. Now let us solve a numerical and find out whether the given data verifies the law of constant proportions or not. In an experiment, 1.03 grams of copper provide 1.288 grams of copper oxide, and in another experiment, 2.938 grams of copper provide 3.672 grams of copper oxide. Show that this data proves law of constant proportions. In first experiment, mass of copper is 1.03 grams and mass of copper oxide is 1.288 grams. By subtracting mass of copper from mass of copper oxide, mass of oxygen is obtained as 0.258 grams. In the first sample of copper oxide compound, mass of copper upon mass of oxygen is 1.03 grams upon 0.258 grams, which is equal to 4:1. In second experiment, mass of copper is 2.938 grams and mass of copper oxide is 3.672 grams. By subtracting mass of copper from mass of copper oxide, mass of oxygen is obtained as 0.734 grams. In the second sample of copper oxide compound, mass of copper upon mass of oxygen is 2.938 grams upon 0.734 grams, which is equal to 4:1. From these two experiments, we can see that the ratio of copper and oxygen elements in the two samples of copper oxide compounds is same, that is 4:1. So we conclude that the given data prove the law of constant proportions. After going through all these examples, it is clear that a given chemical compound has same elemental composition. Now Lisa will repeat the law and the class will listen to her carefully.
A chemical compound always consists of the same elements combined together in the same proportion by mass, independent of the method by which it is prepared or the source from which it is obtained.
Multiple proportions.
According to the law of multiple proportions, when two elements combine to form two or more compounds, the different masses of one element which combine with a fixed mass of the other element.
For example, the mass of oxygen that combines with a fixed mass of carbon, that is 12, bears a simple whole number ratio, that is 16:32 or 1:2. Consider another example. Compounds of sulfur and oxygen. In these two compounds, the ratio of the masses of oxygen that combines with 32 parts of sulfur is 32:48, that is 2:3, which is solve a numerical. Carbon and oxygen are known to form two compounds. The carbon content in one of these compounds is 50%, while in the other compound it is 40%. According to this question, in the first compound, the percentage of carbon is 50. It means that 50 grams of carbon combines with 50 grams of oxygen. Thus, on calculating, we get the amount of oxygen that is equal to 100 grams. Good morning, students.
Good morning, ma'am.
Students, you know atoms of same element or different elements combine in fixed ratio by mass to form various compounds. Do you know that the combination of elements to form compounds is governed by 5 basic laws? Can you name them?
The laws are Law of Conservation of Mass, Law of Definite Proportions, Law of Multiple Proportions, Gay-Lussac's Law of Gaseous Volumes, and Avogadro's Law.
Let us discuss the law of multiple proportions. This law was proposed by John Dalton in 1803. The law states that when two elements combine to form two or more compounds, the masses of one element that combine with the fixed mass of the other element are in simple whole number ratio. Hydrogen and oxygen are two common elements. These elements combine to form two different compounds, namely water and hydrogen peroxide. Water is formed when two atoms of hydrogen combine with one atom of oxygen. Atomic mass of an atom of hydrogen is 1 U and that of an atom of oxygen is 16 U. So, mass of two atoms of hydrogen is 2 U and mass of one atom of oxygen is 16 U. Ratio of masses of hydrogen and oxygen is mass of hydrogen atoms upon mass of oxygen atom, that is equal to 2 upon 16, that is 1:8. Hydrogen peroxide is formed when two atoms of hydrogen combine with two atoms of oxygen. Here mass of two atoms of hydrogen is 2 U and mass of two atoms of oxygen is 32 U. Ratio of masses of atoms of hydrogen and oxygen is mass of hydrogen atoms upon mass of oxygen atoms, that is equal to 2 upon 32, that is 1:16. In case of water molecule, ratio of hydrogen to oxygen is 1:8, while in hydrogen peroxide, this ratio is 1:16. Now if we fix the mass of hydrogen as 2, the ratio of masses of oxygen that combines with hydrogen in water and hydrogen peroxide will be 8:16 or simplified to 1:2. This data proves the law of multiple proportions. Now let us find if we can verify the law of multiple proportions by fixing the mass of oxygen atom in water and hydrogen peroxide. If we fix the mass of oxygen at 16, the ratio of masses of hydrogen that combine with it in water and hydrogen peroxide will be 2:1. Hence, this again proves the law of multiple proportions. So, have you all understood this law?
Yes, ma'am.
Good. Now let us solve a numerical based on this law. When copper oxide is heated, it forms copper and oxygen. In first experiment, when 1 gram of copper oxide was heated, it produced 0.888 gram of copper, and in second experiment, 1 gram of copper oxide gave 0.799 gram of copper. Show that this data prove law of multiple proportions. In first experiment, mass of copper oxide is 1 gram and mass of copper is 0.888 gram. By subtracting mass of copper from mass of copper oxide, mass of oxygen is obtained as 0.112 gram. It means 0.112 gram of oxygen combines with 0.888 gram of copper. to calculate the amount of copper that combines with 1 gram of oxygen. Find the mass of copper upon mass of oxygen. Of oxygen combines with 0.799 gram of copper. To calculate the amount of copper that combines with 1 gram of oxygen, we will calculate by finding the mass of copper upon mass of oxygen, that is 0.799 gram upon 0.201 gram, which is equal to 3.98 gram. The ratio of masses of copper that combines with 1 gram of oxygen is equal to 7.93 is to 3.98, which is equal to 2:1. This is a simple whole number ratio. Hence, it verifies law of multiple proportions. Now Jasmine will repeat the law and the class will listen to her carefully.
When two elements combine to form two or more compounds, the masses of one element that combine with the fixed mass of the other element are in simple whole number ratio.
Law of reciprocal proportions. Learn about the law of reciprocal proportions. The law states that the ratio of masses of two elements that combine separately with a fixed mass of the third element is either the same or some simple multiple of the ratio of the masses in which they combine with each other. Consider three elements, carbon, oxygen and sulfur, that combine to form three different compounds, namely carbon dioxide, sulfur dioxide and carbon disulfide. Carbon dioxide ratio of masses of carbon and oxygen is 12:32. In sulfur dioxide, ratio of masses of sulfur and oxygen is 32:32. The ratio of masses of carbon and sulfur that combines with fixed mass of oxygen, that is 32, will be 3:8. Carbon disulfide ratio of masses of carbon and sulfur is 12:64 or 3:16. Two ratios marked as first and second are related to each other as 1:2, that is, the two ratios are whole number multiple of each other. Hence, it illustrates the law of reciprocal proportions. Solve a numerical. 61.8 grams of carbon combines with 80 grams of oxygen. 30.9 gram of carbon combines with 106.5 gram of sulfur. 13.2 gram of oxygen. To the given data, the mass of oxygen combining with 1 gram of carbon is 1.29 grams and mass of sulfur combining with 1 gram of carbon is 3. Of masses of oxygen and sulfur that combine with fixed mass of carbon, that is 1 gram, is 3:8. The ratio of masses of oxygen and sulfur which combine directly with each other is found to be 3:8. The two ratios are same, hence it illustrates the law of reciprocal proportions.
Gay-Lussac's law of gaseous volume.
According to the Gay-Lussac's law of gaseous volume, when gases react, they do so in volumes that bear a simple whole number ratio to one another and to the volumes of the gaseous products. provided the temperature and pressure remains constant.
Consider the following reaction. The molar ratio for this reaction is 1:3:2. According to Gay-Lussac's law of gaseous volume, the molar ratio of the gases is equal to the ratio of volumes of reacting gases and products. 1 liter of nitrogen gas reacts with 3 liters of hydrogen gas to produce 2 liters of ammonia. Example 1. Formation of water. 2 volumes of hydrogen gas when mixed with 1 volume of oxygen gas give 2 volumes of water vapor at a constant temperature and pressure. Example 2. Formation of hydrogen chloride. 1 volume of hydrogen gas when mixed with 1 volume of chlorine gas gives 2 volumes of hydrogen chloride gas at the constant temperature and pressure. Let us solve a numerical. 40 centimeter cube of methane reacts with chlorine according to the following equation. Calculate the volume of hydrogen chloride gas formed and chlorine gas. According to the question, we have the equation as follows. Since 1 volume of methane requires 2 volumes of chlorine, 40 centimeter cube of methane will require 80 centimeter cube of chlorine. Thus, 80 centimeter cube of hydrogen chloride is formed and 80 centimeter cube of chlorine is required. Avogadro's law.
According to Avogadro's law, under similar conditions of pressure and temperature, equal volumes of ideal or perfect gases contain the same number of molecules.
Dalton's atomic theory. John Dalton, a British school teacher, published his atomic.
In 1803, a famous British chemist, John Dalton, proposed basic theory about the nature of matter. This theory is popularly known as Dalton's atomic theory. Let us learn about the postulates of this theory one by one. According to Dalton, all matter, whether an element, a compound, or a mixture, is made of very tiny particles called atoms. He also interpreted that an atom can neither be created nor destroyed. Atoms of the same element are identical in size, shape, mass, and chemical properties. Atoms of different elements have different sizes, masses, and chemical properties. Here, atoms of hydrogen differ from atoms of oxygen and nitrogen. Atoms of the same or different elements combine together to form molecules or compounds. Atoms combine in the ratio of small whole numbers to form compounds. Atoms of two different elements may combine in different ratios to form more than one compound. The number and kind of atoms in a given compound is always fixed. Later on, more research is carried out, which eventually led to the fact that atoms are made up of still smaller particles, protons, electrons, and neutrons.
Identify the law in which the total mass of the products is equal to the total mass of the reactants during any physical or chemical change from the given options, which are Law of Conservation of Mass, Avogadro's Law, Law of Definite Proportions, Gay-Lussac's Law of Combining Volumes, chemical compound always contains the same elements that are combined together in fixed proportion of mass, irrespective of its source. This statement is true according to which of the following options? Law of conservation of mass, Avogadro's law, law of definite proportions, Gay-Lussac's law of combining volumes. Let us have a quick recap. According to the Dalton's atomic theory, atoms are the building blocks of matter. Combination of different atoms is governed by the basic laws of chemical combination. Such laws are the law of conservation of mass, law of definite proportions, law of multiple proportions, Gay-Lussac's law of gaseous volume, and Avogadro's law.
Mole concept. In this module, we will study about atomic mass, molecular mass, formula mass, molar mass, mole concept, Avogadro's number, and some important formulae. An introduction.
As we know, objects are generally measured by counting or by weight. It is easier to measure large objects like elephants, cars, and eggs by counting. However, it is convenient to measure small objects like rice and butter by weight. For counting common objects, we use a pair of shoes. However, 10 grams of gold coin has billions of gold atoms.
Before discussing about mole, let us understand some basic terms like atomic mass. Atomic mass. In the 19th century, scientists adopted a comparative method to find the atomic mass.
Atomic mass of an atom is a number that compares the mass of a given atom with the 1/12 of C12 atom. One atomic mass unit is defined as the mass exactly equal to 1/12 of the mass of one carbon-12 atom.
Consider the following example. One atomic mass unit is equal to 1.66056 into 10 raised to the power minus 24 grams. Mass of hydrogen atom is equal to 1.6736 into 10 raised to the power minus 24 grams. Average atomic mass. Many naturally occurring elements exist as more than one isotope. On taking the account of these isotopes and their percentage occurrence, the average atomic mass instead of atomic mass is considered. To calculate the average atomic mass of an atom, exact atomic mass of its each isotope is multiplied by its percent abundance. The results are added together and rounded off to an appropriate number of significant figures. Calculate the average atomic mass of carbon from the given table.
Molecular mass is the mass of the formula unit or sum of the atomic masses of the atomic species as given in the molecule.
Calculate the molecular mass of methane. Formula mass.
Formula mass is the sum of the atomic masses of the atomic species as given in the formula of the compound.
For example, the formula mass of sodium chloride is expressed as the sum of atomic mass of sodium and atomic mass of chlorine. Let us calculate the formula mass of sulfuric acid. "98 grams of sulfuric acid is equivalent to 1 mole of sulfuric acid. Molar mass.
Molar mass is the mass of 1 mole of a substance in grams.
Mole concept. In the SI system, a mole is the base quantity for the amount of substance. So you must be wondering how big a mole is. A mole is a collection of 6.023 into 10 raised to the power 23 particles. These particles may be atoms, molecules, ions, or electrons. 1 mole of marble would be enough to cover the entire earth to a depth of 50 miles. If the entire population of the earth were to do nothing but count atoms in 1 mole of an element 24 hours a day at the rate of 1, yet there is just 1 mole of water molecule, that is 6.023 into 10. A mole is a large number because atoms, molecules and formula units are quite small. In order to have useful masses in lab, we have to use moles of those substances.
The birthday party will be without balloons. We can easily count the number of balloons used in a birthday party. But can we count the number of particles of gas present inside each balloon? Let's try. This balloon is filled with oxygen and this one with nitrogen. If the volume is same in both of them, then which one will have more number of particles of gas? The answer to this question can be given with the help of mole concept. Mole concept was given by Amedeo Avogadro, which states that equal volumes of gases at the same temperature and pressure contain equal number of molecules. Let us find 1 mole of which of these gases, hydrogen, ammonia and carbon dioxide, has more number of molecules. It is observed that 1 mole of all of these gases have 6.022 into 10 to the power 23 molecules. Let us try to find 1 mole of which of these gases will occupy more volume. Since the volume of substance changes with temperature and pressure, we measure the volume of all the gases at STP, that is 273 Kelvin and 1 atmospheric pressure. First, we will measure the volume of 1 mole of hydrogen gas. You will observe that it occupies 22.4 liter at STP. When we measure the volume of 1 mole of ammonia gas, we observe that it occupies 22.4 liter at STP. Similarly, when we measure the volume of 1 mole of carbon dioxide at STP, it also occupies 22.4 liter. Let us weigh 1 mole of each of these gases and find if their weights are also identical like their volumes and number of particles are. First, we will find the weight of 1 mole of hydrogen gas. It weighs 2 grams. When we weigh 1 mole of ammonia, it weighs 17 grams. When we weigh 1 mole of carbon dioxide, it weighs 44 grams. The following equation shows how 1 mole of substance is related to the number of molecules. Volume of substance,
Avogadro's number. The number of particles in 1 mole of a substance, whether an element or compound, is known as the Avogadro's number. It was found by Amedeo Avogadro. The relationship between the gram atomic weight and the Avogadro's number for some common elements is as follows. Important formulae.
Some important formulae related to mole are as follows. Here are some important relations for solving questions. Some more important relations useful in the calculations are as follows.
Let us solve a numerical. Calculate the number of each kind of atoms in 5.5 grams. Now, one formula unit of sodium carbonate contains 2 atoms of sodium, 1 atom of carbon and 3 atoms of oxygen. Therefore, the number of sodium atoms in 5. Let us solve another numerical. A cylinder contains 0.30 grams of ethylene. Calculate the. Let us begin with the first part. The molecular mass of ethylene is 28. Now we will solve the third part. One molecule. Let us solve one more numerical. How many gram molecules and grams of ammonia are present? Now we will calculate the gram molecular mass of ammonia, which comes out to be 17. Therefore, 1 gram molecule of ammonia. It's time to test your knowledge. Complete the following. Avogadro's number represents the number of atoms in. The options are A. 12 grams of C12, B. 320 grams of sulfur, C. 32 grams of oxygen, D. 12.7 grams of iodine. Complete the following. 1 mole of water corresponds to which of the following options? A. 22.4 liters at 1 atmosphere and 25 degrees Celsius, B. 1 gram, C. 18 grams, D. 6.02 into 10 raised to the power 20. From the given options, identify the number of water molecules present in a drop of water weighing 0.018 grams. The options are A. 6.023 into 10 raised to the power 26, B. 6.023 into 10 raised to the power 23, C. 6.023 into 10 raised to the power 20, D. 6.023 into 10 raised to the power 90. Complete the following. 1 mole of oxygen gas is the volume of, and the options are A. 1 liter of oxygen at STP, B. 22.4 liters of oxygen at STP, C. 32 liters of oxygen at STP, D. 6.02 into 10 raised to the power 23 molecules of oxygen. Let's have a quick recap. The atomic mass of an element is expressed relative to C12 isotope of carbon, which has an exact value of 12U. Molar mass is the mass of 1 mole of a substance in grams. The empirical formula and molecular formula. In this module, we will study about percentage composition, empirical formula, determination of empirical formula, molecular formula, determination of molecular formula, and chemical equations. An introduction.
Hooray! I scored 410 marks out of 500.
Percentage composition. A percentage composition of a compound is the percentage by weight of each element present in it. The steps to calculate the percentage composition of an element in a compound are: identify the elements present in the compound, add all the mass contributions. The steps to calculate the percentage composition of an element in a compound are: identify the elements present in the compound, add all the mass contributions calculated in step 3 to find the molecular mass of the compound. Thus, the expression for the percentage composition for an element is total mass of the element in one molecule upon gram molecular mass of the compound in 200. Let us try one question. Calculate the percentage composition of carbon in glucose. The question can be solved by following the given series of steps. Step 1. Identify the elements present in. Step 3. Calculate the mass contribution of each element present in glucose. The total mass of carbon is equal to the product of the number of carbon atoms. The total mass of oxygen is equal to the product of number of oxygen atoms and the atomic mass of oxygen, which is equal to 96. Step 4. Find the molecular mass of compound. Step 5. Expressing the molecular mass in terms of gram molecular mass. Thus, the gram molecular mass is equal to 1. Step 6. Find the percentage composition of carbon in glucose. Let us solve a numerical. Calculate the percentage composition of ammonium hydroxide. We will first calculate the molecular mass of ammonium hydroxide, which is as follows. The percentage composition of nitrogen on calculating the percentage composition of hydrogen Empirical formula.
The empirical formula of a compound is the simplest formula, which gives the simplest ratio in the whole numbers of atoms of different elements present in one molecule of the compound.
For example, the molecular formula of hydrogen peroxide is H2O2. Let us consider another example. The molecular formula of glucose is
Empirical formula mass is the sum of the atomic masses of all the elements present in the empirical formula.
Determination of empirical formula.
Steps to determine the empirical formula are as follows. Step 1. Add the percentages of all the elements and subtract them from 100. The result will be the percentage of oxygen present in the compound. Step 3. If the molecule contains water of crystallization, then its percentage weight is divided by the molecular mass of water, that is 18. In case the result of step 4 is too far to be rounded off, then multiply each number obtained in step 4 by the same factor to get the lowest whole number multiple. Step 5. Empirical formula is now derived by writing the symbols of various elements side by side with the number of atoms of each one as the subscript to the lower right of its symbol.
Let us solve a numerical. An organic compound, after analysis, was found to have the following percentage composition. Hydrogen equal to 6.7%. The numerical can be solved by following the given series of steps. To calculate the empirical formula, let us make the given table. Let us write the given information about carbon in the table. Now write the information about hydrogen. Let us write the given information of oxygen. Let us calculate the number of atoms of carbon, hydrogen and oxygen by dividing the percentage mass by atomic mass. Hence, the empirical formula of the organic compound is CH2O. Let us solve another numerical. Find the empirical formula of the compound with the following percentage compositions. Carbon 82.7% and hydrogen 17.3%. The given numerical can be solved by following the given set of steps. The total percentage of the compound is. Now, to get the empirical formula, write the symbol of the elements present followed by the numbers obtained as the simplest ratio on the right-hand side as subscripts. Molecular formula.
The molecular formula of a compound denotes the actual number of atoms of different elements present in one molecule of the compound.
Consider the following example. The molecular formula of calcium carbonate is CaCO3. Consider another example. The molecular formula of blue vitriol is CuSO4. Determination of molecular formula. Steps to find the molecular formula of a compound are: Step 1. Calculate the empirical mass of the compound from its empirical formula. Thus, the molecular formula is equal to N into empirical formula, where N is equal to the molecular mass by the empirical formula mass. Let us consider an example. The empirical formula of hydrogen peroxide is HO, and its empirical formula mass is 17. However, its molecular mass is. Let us solve a numerical. The molecular formula of a compound is C8H6O4 and its empirical formula mass is 83. We need to calculate, given the molecular formula of a compound is C8H6O4. We know that N is equal to the molecular mass by empirical formula mass. Thus, the empirical formula is calculated with the help of the given expression. Chemical equations.
A chemical equation is a balanced account of a chemical transaction. A balanced chemical equation has an equal number of atoms of different elements in the reactants and products.
Consider the following reaction. We will now write the number of all the atoms present in the reactants as well as products and compare. Let us learn the steps for balancing a chemical equation. Consider the following example of unbalanced chemical equation. We will now write the number of all the atoms present in reactants as well as products and compare. Multiply the number of hydrogen atoms by 2 in the above equation to balance the number of hydrogen atoms. Steps for solving such problems are: Step 1. Write a balanced chemical equation for the reaction. Step 3. Write down the product of 22.4 liters and the number of molecules below each gaseous substance. Let us have a quick recap. The empirical formula of a compound is the simplest formula which gives the simplest ratio in the whole numbers of atoms of different elements present in one stoichiometry. In this module, we will study about stoichiometry, general stoichiometric steps, mass-mass relationship, mass-volume relationship, volume-volume relationship, and limiting reagent. An introduction to stoichiometry.
I love to eat Maggi noodles.
Do you know what makes Maggi more tastier and a preferred choice over the other brands?
Composition is of great importance. A little change in the composition may give us a different product.
Stoichiometry. Stoichiometry is derived from the Greek words stoichion, which means element, and metron, which means measure. Jeremias Benjamin Richter from Germany first introduced the term stoichiometry in chemistry in the late 19th century. Stoichiometry deals with the relative quantities of reactants and products in the chemical reactions. Consider the following reaction. It gives the complete information about the reaction under consideration. It tells that 1 mole of zinc reacts with 2 moles of dilute hydrochloric acid to form 1 mole of zinc chloride and 1 mole of hydrogen gas. These stoichiometric coefficients are useful since they establish the mole ratio between the reactants and the products. General stoichiometric steps.
General stoichiometric steps are as follows. Step 1. The balanced chemical equation is written in the molecular form. Step 3. The atomic weights, moles, molar volumes of the underlying substances are written depending upon the nature of the problem. For those substances whose weights, volumes have to be calculated, the sign of interrogation is written.
A balanced chemical equation conveys the quantitative information which helps in a number of calculations. Mass-mass relationship.
Mass relationship. The mass of one of the reactants or the products is given, and the mass of some other reactants or products is to be calculated.
Steps to follow while solving a problem based on mass-mass relationship. In a mass-mass relation problem, the mass of one of the reactant or product is given. Step 2. Taking the ratio from the balanced chemical equation, we calculate the number of moles of the second reactant or product. Let us solve a numerical based on mass-mass relation. Determine the amount of sulfuric acid, 75% by weight, which is required to decompose 0.5 mole of calcium carbonate with the help of the given data. The numerical can be solved by following the given series of steps. Step 1. Write the balanced chemical equation. Step 3. Calculate the molecular mass and mention the actual quantities. Step 4. Convert the moles of calcium carbonate in mass in grams. Therefore, on calculating, we get that 50 grams of calcium carbonate is decomposed by 49 grams of sulfuric acid. Mass-volume relationship.
In mass-volume relationship, mass volume of one of the reactants or products is given, and the mass volume of the other is to be calculated.
Steps to follow while solving a problem based on mass-volume relationship. In a mass-volume relation problem, the mass of Step 2. Take the ratio from the balanced chemical equation to calculate the number of moles of second reactant or product. Solve a numerical based on mass-volume relation. What volume of hydrogen will be produced when 9 grams of iron reacts with an excess of sulfuric acid? The numerical can be solved by following the given series of steps. Step 1. Write the balanced chemical equation. Step 3. Convert grams of iron into moles. Step 5. Convert moles of hydrogen into volume. Thus, 3.84 decimeter cube of hydrogen will be produced when 9 grams of iron reacts with an excess of sulfuric acid. Volume-volume relationship.
in volume-volume relationship. The volume of one of the reactants or the products is given and the volume of the other is to be calculated.
Let us solve a numerical based on volume-volume relation. Calculate the volume of oxygen that is necessary. The numerical can be solved by following the given series of steps. Step 1. Step 3. Calculate the molar volume and mention the actual quantities. Therefore, on calculating we get that 5 liters of butane at NTP will require 32.5 liters of oxygen at NTP. What would you get if 2 slices of bread and a slice of cheese are combined together? How many sandwiches can be made if 6 bread slices and 2 pieces of cheese are available? We get 2 sandwiches and 2 breads are left.
The reactant that is entirely consumed and limits the amount of product formed by the completion of a reaction in a chemical reaction is called the limiting reagent.
NO and O2 react in 2:1 ratio in order to form the product. The expression for the identification of limiting reagent is as follows. Let us solve a numerical. In an experiment, a mixture of 0.5 mole of methane was burnt in 2.0 moles of oxygen in a sealed steel vessel. According to the balanced chemical equation, 1 mole of methane reacts with 2 moles of oxygen to produce 1 mole of carbon dioxide and 2 moles of water. Now, 1 mole of methane produces 2 moles of water and 0.5 mole of methane will produce 1 mole of water.
Limiting reagent. The reactant, which is consumed during a reaction and consequently limits the reaction, is called a limiting reagent. Let us take an example to understand how a limiting reagent limits a reaction. When atmospheric nitrogen and oxygen react at a very high temperature, nitric oxide is formed. Nitric oxide is quickly oxidized to nitrogen dioxide by atmospheric oxygen. The bulb on the left side of screen contains nitric oxide and that on the right side contains oxygen. In first case, 4 molecules each of nitric oxide and oxygen are present separately in 2 bulbs. When these are allowed to react, 4 molecules of nitric oxide react with only 2 molecules of oxygen and 2 oxygen molecules remain unreacted. The reaction stops when nitric oxide gets consumed, that is, nitric oxide limits the reaction and therefore it is the limiting reagent while oxygen in this reaction is in excess. In second case, 6 molecules of nitric oxide and 3 molecules of oxygen are present separately in 2 bulbs. When these are allowed to react, 6 molecules of nitric oxide react with 3 molecules of oxygen. There is no unreacted molecule in the bulbs. In third case, 6 molecules of nitric oxide and 2 molecules of oxygen are present separately in 2 bulbs. When these are allowed to react, 2 molecules of oxygen react with only 4 molecules of nitric oxide and 2 nitric oxide molecules remain unreacted. This time reaction stops when oxygen gets consumed, that is, oxygen limits the reaction and therefore it is the limiting reagent while nitric oxide in this is in excess.
Let's have a quick recap. Stoichiometry is the quantitative relationship among the reactants and the products. The problems involving these calculations may be classified as mass-mass relationship, mass-volume relationship, and volume-volume relationship. Limiting reagent is a reactant in a chemical reaction that is entirely consumed and limits the amount of product formed by the completion of a reaction. Volumetric calculations. In this module, we will study about solution, percentage, molarity, molality, normality, mole fraction, and parts per million. An introduction.
There are two test tubes, A and B, containing copper.
The other difference that we see is that the solution in test tube A is more concentrated as compared to the solution in test tube B.
The concentration of these solutions is determined by using
Solution. Solution is a homogeneous mixture of two or more chemically non-reacting species whose composition can be varied within certain limits. A solution consists of a solvent and a solute. Solute is the component of solution present in a lesser amount.
Many of us enjoy a black coffee. It is a homogeneous mixture prepared by mixing and heating different ingredients like coffee, sugar, and water. When we mix and heat these ingredients, it is not possible to identify the ingredients present in the mixture because sugar and coffee seem to disappear. It results in formation of solution which is a homogeneous mixture. A solution is a homogeneous mixture of two or more substances whose composition can be varied within certain limits and the components cannot be seen with the naked eyes. Do you know we come across many solutions in our everyday life? Oceans, lakes, soft drinks, and soap solutions are various examples of solutions. The air we breathe is a solution of several gases, and various fluids running in our bodies are also solutions. So we can say solutions are important to us.
Concentration of a solution.
A solution having lesser amount of solute is termed as a dilute solution. The solution having comparatively more amount of solute is known as If we add 1 gram sugar in a beaker A containing 250 milliliters of water and add 10, the concentration of a solution can be expressed better quantitatively. The concentration in percentage can be expressed in three ways: mass percentage, volume percentage, and mass by volume percentage.
Mass percentage is the mass of a solute in grams dissolved per 100 grams of the solution. Consider the following example. 10% by mass of sodium chloride solution means amount of sodium chloride is equal to 10 grams and the amount of solution is equal to 100 grams. Mathematically, mass percentage is expressed as follows. Mass percentage of solute is equal to mass of solute upon the sum of mass of solute and mass of solvent into 100.
Let us solve a numerical. If I dissolve 20 grams of sucrose in 200 grams of water, what will be the mass percentage of sucrose in the solution? We have mass of sucrose dissolved, which is equal to 20 grams, and the mass of solvent is equal to 200. Thus, on applying the expression and substituting the values, comes out to be 9.09. If W is equal to the mass of the solute in grams, V is equal to the volume of the solution in centimeter cube, M dash is equal to the molecular mass of the solute in grams per mole, M is equal to the molarity of the solution in moles per liter, then we have number of moles of solute is equal to the mass of the solute The expression of molarity now becomes as follows. Point to note. Equation 2 gives the relation between the molarity of the solution with the mass of the solute in grams, volume of solution in centimeter cube, and molecular mass in grams. Do you know that the formula of molarity involves volume, which depends on temperature? Relationship between volume and molarity. If V1 milliliters of a solution of molarity M1 is diluted to volume V2 milliliters and the molarity of the diluted solution is M2, then it is expressed as M1 into V1 is equal to M2 into V2. The molarity equation for reaction between the two reactants is as follows. Here, N1 is equal to the number of moles of reactant 1 and N2 is equal to the number of moles of reactant 2.
Let us solve a numerical. Calculate the molarity of the solution prepared by dissolving 12 grams of sodium. The given numerical can be solved by following the series of steps. The expression for calculating molarity is as follows. Step 2. Calculate the number of moles present in 12 grams of sodium hydroxide using the given expression. Step 3. Determine the volume of solution in liters. Here the volume of the solution is equal to 0.600 liter.
Molality.
Molality is defined as the number of moles of a solute dissolved per 1000 grams of the solvent.
If mass of solute is equal to W dash grams, molecular mass of solute is equal to M dash grams per mole. Mass of solvent is equal to W grams, which is equal to W by 1000 kilograms. Molality of the solution is equal to M mole. Let us solve a numerical. A solution of potassium. Step 1. Calculate the molecular mass of the solute, that is, potassium carbonate. This comes out. Step 2. Calculate the number of moles present in 25 grams of potassium carbonate. Step 3. Determine the mass of the solution. We are given the density of the solution as 1 gram per milliliter. And Step 4. Determine the mass of the solvent. According to the formula, the mass of solution is equal to the mass of solute plus mass of solvent. We have mass of solution, which is equal to 600 grams, and the mass of solute as 25 grams. Step 5. Determine the molality of the solution. We already have calculated the number of moles of potassium carbonate, that is 0.18 mole, and the mass of solvent as 575 grams, which is equal to 0.575 kilograms. Do you know a solution containing 1 mole of solute per 1000 grams of the solvent is known as a molar solution? Molality is considered a better term for expressing the concentration of solution as compared to the molarity. In molarity, we consider the volume of the solution that changes with the temperature due to the expansion and contraction of the liquid with the temperature. Normality.
Normality is defined as the number of gram equivalents of a solute dissolved in per liter of a solution at a particular temperature.
The equivalent mass of a solute expressed in grams is called gram equivalent. Thus, the gram equivalent of solute is equal to the mass of solute upon equivalent mass of the solute. If W grams of a solute with the equivalent mass E is present in V centimeter cube of a given solution, then the expression for normality is
Equivalent mass is the mass of a substance that combines with or displaces 1.008 parts by mass of hydrogen or 8 parts of oxygen or 35.5 parts of chlorine by mass. Given are the formulae for expressing equivalent mass. Some more formulae for expressing equivalent mass are as follows.
Let us solve a numerical. Calculate the volume of 0.2 normal acid required to neutralize 20. We are given the normality of acid is equal to 0.2 N. The normality of sodium hydroxide is equal to N by 20. The volume of sodium hydroxide. Therefore, the volume of an acid can be calculated as follows. The volume of acid required to neutralize 20 milliliters of N upon 20 of sodium hydroxide is equal to 5 milliliters. Relationship between molarity and normality can be expressed as follows. For acids, normality is equal to the product of molarity and basicity. Let us solve a numerical. Calculate the normality of a solution that is prepared by dissolving 0.36 gram of oxalic acid in water. If we know that the normality is equal to the number of gram equivalent of solute upon the volume of solution in liters. For calculating normality, we will follow Step 2. Calculate the equivalent mass of the solute, that is, oxalic acid, with the help of the given expression. Step 3. Calculate the number of gram equivalents of the solute, that is, oxalic acid dissolved with a. Step 4. Calculate the volume of solution in liters. Volume of solution is equal to 200 centimeter cube. As we know, 1 liter is equal to 1000 centimeter cube. Therefore, the volume of solution in liters is equal to 0. Step 5. Calculate the normality of oxalic acid with the help of the given expression. Mole fraction.
Mole fraction is the ratio of the number of moles of a particular component to the total number of moles of all the components present in the solution.
Mathematically, mole fraction of a component is equal to the number of moles of the given component upon the total number of moles in a solution. For a binary solution of component A and component B, the mole fraction of each can be calculated as follows. The sum of mole fractions of all the components present in a solution is always equal to 1. Let us solve a numerical. Determine the mole fraction of each component in the solution containing 30% water, 30% ethanol, and 40% acetic acid by mass. We know the formula to express the mole fraction of a component, which is as follows. Now we will proceed further. Step 1. Convert the percentage mass of each component present in solution into grams. Step 2. Calculate the molecular mass of each. The molecular mass of acetic acid is equal to 60 grams per mole. The number of moles of ethanol on calculating comes out to be 0.65 mole. Similarly, the number of moles of acetic acid is also calculated. The number of moles of acetic acid on calculating comes out to be 0.66 mole. Step 5. Calculate the mole fraction of each component present in the solution using the given formula. As we know that the mole fraction of ethanol is equal to the number of moles of ethanol upon the total number of moles. Similarly, the mole fraction of acetic acid can be calculated, which is equal to the number of moles, parts per million.
Parts per million is defined as the mass of solute in grams present in 1 million, that is 10 to the power 6 grams of the solution. 7 parts per million of calcium carbonate solution means that 7 grams of calcium carbonate is present in 10 to the power 6 grams of solution. The following animation will summarize about the various concentration terms.
John is feeling very tired. So he decides to take glucose solution to get instant energy. He mixes 2 teaspoons of glucose in a glass of water and drinks it.
John, how are you feeling now?
Now I am feeling good and energetic.
Can you prepare the glucose solution of the same concentration for me, as I am also feeling low today?
Same concentration? Yes. Why not?
Son, before preparing the glucose solution of the same concentration, you must know how many grams of glucose you dissolved earlier in how many milliliters of water.
I don't know.
Solutions of the same concentration can only be prepared if we know the quantity of the solute and the solvent.
Now I understood.
Let's correlate the concept of concentration with our day-to-day life.
We use rupee in India, but when we go to America or Britain, we use dollar or pounds. These are all different forms of currencies used to express money. Similarly, concentration of a solution can also be expressed in various ways. Let us learn about them. The mass percentage of a component of a solution is defined as the amount of solute present in 100 gram of the solution. The volume percentage is defined as the amount of solute present in 100 milliliter of the solution. The mass by volume percentage is defined as the amount of solute present in 100 milliliter of the solution. Parts per million is a unit to express the concentration of trace amount of solute in a solvent. Mole fraction is the ratio of number of moles of one component to the total number of moles present in a solution. Normality is defined as the number of gram equivalents of solute present in 1 liter of solution. Molarity is defined as the number of moles of solute dissolved in 1 liter of the solution. Molality is defined as the number of moles of solute dissolved in 1 kilogram of solvent.
Now John, you have learnt about different concentration terms.
Can you tell me, out of molarity and molality, which concentration term is better to express the concentration of any solution?
I don't have an idea.
The answer is very simple. Molality is a better concentration term than molarity. You know that molality is moles of solute per kilogram of solvent and molarity is moles of solute per liter of the solution. Molarity is temperature dependent, whereas molality is independent of temperature. So, when the temperature of the solution increases, volume of a solution increases, and heating makes the solution's molarity go down, but the molality remains unchanged.
That's interesting. Now, I will revise the formulas of the concentration terms.
Choose the concentration term that is independent of temperature. The options are A. Molarity, B. Molality, C. Normality, D. Weight by volume percentage. Identify the quantity that is used in normality of the solution. The options are A. Number of gram equivalents, B. Number of moles, C. Number of formula weights, D. Number of atoms. Complete the following. The sum of mole fractions of all the components present in the solution is always, the options are A1, B2, C3, D4. Identify the term generally used to express the concentration of atmospheric pollutants in cities. The options are A. Normality, B. Molarity, C. Formality, D. Parts per million. Let's have a quick recap. A solution is a homogeneous mixture which is composed of solute and solvent. The amount of substance present in a given volume of a solution is also expressed in other concentration terms such as parts per million, molarity, molality, normality. Molality is the number of moles of solute dissolved per 1000 grams or 1 kilogram of the solvent.